This is the third and final part of Lesson 26 in heat transfer. In Lesson 26, we have been discussing thermal radiation heat transfer in a large isothermal enclosure. In the last lesson, we saw why this idea of a large isothermal enclosure is so beneficial. If a surface or an object is situated in a large isothermal enclosure, the radiation heat transfer incident on the surface or the object is known to be blackbody radiation, characterized by a spectral distribution equivalent to blackbody emission from a surface whose temperature is the same as the temperature of the walls of the enclosure. The power of this simplification cannot be understated. It enables the solution of a vast array of radiation heat transfer problems. Because it is so important, in this part of the lesson, we will prove to ourselves that the radiation streaming in a large isothermal enclosure is indeed blackbody radiation at the temperature of the walls of the enclosure. By the end of this lesson, you should be able to prove that the radiation streaming in a large isothermal enclosure is blackbody radiation, and that the blackbody radiation has a spectral distribution equal to that associated with emission from a surface at the temperature of the walls of the enclosure. On with the final part of Lesson 26.
The proof of this statement, right, which is the statement that we apply, this theorem that we apply when we get this equation that applies to 90% of radiation problems, is that the radiation streaming through an enclosed space with walls at a uniform temperature is blackbody radiation corresponding to a temperature of the walls. The radiation is sigma TW to the fourth, crossing any unit area in the space. And then this is the key thing, the walls may be black or non-black. So it doesn't matter what the nature of the walls are. Surroundings can be whatever you want. The proof of this, I think, was most famously demonstrated by a man named Ephraim Sparrow. Have you heard that name before in either my class or Professor Penske's class? Ephraim Sparrow? No? Okay, so Ephraim Sparrow, he'd like to be called Eph. So I'm going to say Eph was probably the most prolific heat transfer researcher in the last 50 years, I would say. So he contributed more to the field of heat transfer probably than anybody else did. He has like a bajillion publications. He spent his entire career working on advancing the field of heat transfer, and in particular radiation. He's an interesting guy. I had the opportunity to meet him and work with him a little bit. He worked at the University of Minnesota for a very long time. I will say this about him, hopefully to convince you that we should pay attention to what he says. He got a PhD from Harvard right after he finished his bachelor's degree at Princeton. And then he decided that the PhD from Harvard wasn't good enough, so he went to MIT and got a second PhD from MIT. In between the Harvard PhD and the MIT PhD, he had a little stint where he worked as a consultant, and he solved a problem for the Arizona Public Utility Commission, which I'll share that story on Monday. But just know that, so Eph is the one who presented this proof of this idea to me for the first time, and so I have been sharing that back to you all students since I received that proof from him. Okay, so he was this incredibly prolific guy that you would never know it in interacting with him. He was the most humble, generous, sweet person that I think I've ever met that has been that prolific in their output. So here is his proof. Okay, so this is 100% attributed to Ephraim Sparrow. He died about a year ago. So this is the theorem. We want to prove it. So he said, okay, we can prove it in 3 steps. Step 1, we have to prove that the radiation is the same in all directions. That's an important part of this. It's sigma t to the fourth processing any unit area in the space. So that means it doesn't matter how I orient my surface, right? It's still black body radiation at sigma t to the fourth. Okay, so to prove this, he said, well, pretend that it's not the case that the radiation is the same in all directions. And let's see what happens if it's not the same in all directions. So he said, okay, so draw, your big isothermal enclosure, which he would always draw as an egg. And he'd say, look, you're telling me that the temperature of the walls of that enclosure are, yeah.
Should we be trying to write this?
No, just take it in, okay, yeah. The important thing is what I wrote before this. This is just for your perhaps enjoyment, or if you're not enjoying it, then just tune out, okay? This is just trying to convince you that we can make this substitution and that this assumption allows us to say that G is equal to sigma t to the fourth. You say, okay, start by assuming that the opposite is not true. So you have all of these walls are at TW, and they represent a thermal reservoir, right? Energy can come from the walls at one temperature. So imagine putting two surfaces on the inside of this isothermal reservoir, right? And what you're telling me is if it's not true that the radiation is the same in all directions, then if I have some radiation incident on that surface and some radiation incident on this surface, if these are not the same, it must be that the temperatures of these surfaces are not the same. And right? So they're different, which would mean that I could run a heat engine between the two. I could connect a little heat engine between these two surfaces, right? Drive a little Carnot engine, for example, by taking energy from one and turning some of that thermal energy into work and rejecting energy to the other. That cannot happen because I'm sitting inside of an isothermal reservoir, right? All of the energy is coming from one isothermal reservoir. You can't run a heat engine on a single thermal reservoir. That violates the second law. So this can't be true. It can't be true that the radiation is different in different directions. That was step one. So now we know the radiation is the same in all directions. It has to be that it's the same in all directions. And more practically, why does that happen? It's because we have multiple internal reflections off of the walls, and the multiple internal reflections tends to spread everything out. So it gets all evened out in all directions. Okay, then he said, all right, that's step one. Step two, you got to prove that if you put a little black body surface inside of the enclosure, that it comes to the same temperature as the walls. So he's like, okay, so draw your blob again. Let's say here's your blob. The blob has one temperature. And now imagine, and he would always say, hang a little black body surface from a magic string that allows the thing to stay on the inside, but it doesn't, there's no communication of information with the outside world. So it's a magic string that holds the thing in the place, but doesn't actually connect it with the walls. So then he said, okay, if you assume that this thing does not come to the temperature, the same temperature of the T wall, right? So if TS is not equal to TW, then again, we could run a heat engine between, right, the wall and this little thing and produce some work. But that's impossible because this is completely isolated from the environment, right? It has to be that it comes to the same temperature as the wall, and or else we'd be able to run a heat engine between the two, and you can't do that. That violates the second law. So again, more practically, I think if objects come into thermal equilibrium, right? So like it makes sense that eventually the thing is going to come to the same temperature as the walls if the walls rise. Okay, then the last step in his proof was he said, okay, given the first two things, let's do an energy balance on a little sphere. All right, so here is the sphere. He's already convinced us that, or at least he convinced me when I heard him do this for the first time, that the temperature of the sphere must be the same as that as the walls, or else we would have violated the second law. He's also already convinced me that the radiation that's incident is the same in all directions. So it's the same whether I draw it this direction, or this direction, or this direction, or this direction, or this direction. It's the same over the entire surface because the direction doesn't matter. Okay, so then I'm going to do an energy balance on this thing. So here is the control surface, and I have in addition to the incident energy, which could be absorbed, and it's going to be all absorbed, right? I have some emitted energy. So I'm absorbing GA because I'm absorbing everything. It's a flat body surface, and I'm emitting. So the energy balance says E dot stored is equal to E dot in minus E dot out plus E dot gen. There's no generation, and we're assuming steady state conditions. Right, so what goes in must come out. So I have absorbed coming in, the absorbed stuff. What I have going out is the emitted stuff. Right. So the absorbed must equal the emitted stuff. Well, the absorbed stuff is G times A, right? Because I'm absorbing everything that's incident on the surface. And the emitted stuff is that of a black body surface. So it's being emitted like that, sigma TW to the fourth. It's the same area. So G is equal to sigma T wall to the fourth. Right? This is a Latin thing that I don't remember, but it means therefore it is proven. QED. So we just proved it. So G must be equal to sigma T wall to the fourth if we're in a large isothermal enclosure where the isothermal part, the temperature is equal to whatever the temperature of the walls are. Sometimes we call it the temperature of the surroundings. Okay, so it's proven then, and this idea works, assuming we have a large isothermal enclosure. And it doesn't matter whether the walls are black bodies or not. We didn't have to say anything about the nature of the walls in order to make this proof. The walls can be black body surfaces, or they don't have, it doesn't matter. They could have an emissivity of 0.000001. It doesn't matter. We'll still have black body radiation streaming around inside of the enclosure. That's a really, really powerful statement. Okay, and it allows you to do a lot of work, right, with this equation.